analytics, data mining, computational biology, and effective computing with numerous publications in reputed international journals and conferences. She has also served as a principal investigator and co-investigator for several government-funded research projects and is an active academic leader and mentor. We are privileged to have her with us today, and we are confident that her session will be both insightful and inspiring. It is a great honor to welcome Dr. M.V. Chudi to today's session. A heartfelt welcome to all the participants, faculty members, and students joining us today. Let us begin the session.
Good morning.
Good morning, ma'am.
Yeah, I just wanted to check if I'm audible.
Yeah, audible.
Okay, so I will start the presentation. Kindly tell me if it's visible. Huh?
Okay, ma'am.
Is it visible?
Yes, ma'am, visible.
Okay, so I can start, I think, no? So today is the final day for the FDP. And I understand that there are around 75 participants. So I will continue. If in case if it breaks, I think can you just mention, can you just call me on the WhatsApp or message me?
Okay, ma'am.
Okay. Okay. So I hope you had a 5 days session on LLMs and then different prompting techniques, RAG, and so on. So today we are moving into a little bit different one. That is also a generative AI model, which is actually called as a diffusion models. So what I have planned is that there are a lot of work that has happened with diffusion models, and maybe few of you have worked on it also. But I will just cover basic things. I have not, one second. I don't have a index slide, but I will just tell you, I will just talk about what is meant by a diffusion model and where this idea has basically come from, and what are the advantages of using diffusion models, and especially when you want to generate images. What are the different types of diffusion models? Because people may be confused with these terms that we talk about. Sometimes we talk about latent diffusion model, stable diffusion. Then we don't know what DALI is. Is that a diffusion model? So just an overall classification of what is a diffusion model. And we look into very famous diffusion models that has come out. The very first one we will discuss a little bit in detail, because that is where the actual idea originated. And then from there on, you can see that a lot of work is being carried out, lot of refinements and then lot of modifications are done to the base algorithms. They even unify this LLM with the diffusion models. Like in stable diffusion, they use a clip kind of an LLM based training and so on. And then if possible, if time permits, we can just see a demonstration of how the basic DDPM or DDIM works with a set of images. So this is the plan that I have, and we'll just continue, and you can just ask me or discuss if you have anything in between. So what is exactly diffusion? So now I can tell you that it's also a generative AI model, definitely. And from there, this term has come out. What is meant by diffusion? This diffusion is a normal term. You would have heard it in systems like, in physics or chemistry and biology. Everywhere we have heard about this diffusion. Okay, it's what you decide only. It's just the process of this particles or information or energy moving from an area of high concentration to an area of lower concentration. That is always we know when there is a chaos or we have an interrupted, disturbed, perturbed system, always this tries to reach its equilibrium. So concentration becomes uniform throughout the system. So, and then we know when it is in a stable state, the energy is minimum. So this is the process of diffusion. Like for example, if we have, that is what is shown in the slide. Suppose we have a glass of water and then we are trying to drop an ink onto it. Initially, you can see that it is highly concentrated on that point where we have dropped the ink. And slowly from higher concentration, it dissolves and diffuses into a uniform throughout the system. That is what is given here. So this is the concept that people used here. It is a law of thermodynamics that the system reaches its stable state. So there are other, we have also heard about other law of thermodynamics are being used here, like we have heard about Boltzmann's machine, all which models this in neural networks. So they have given another example also. Suppose you spray something on somewhere and then it disperses as time passes by. So what is important is it automatically does this with respect to the time. So now if you see here, there is one property that we are following, okay, very importantly based on this. So if you look at the movement of this molecule, okay, it may be whatever is the case. It could be an information or energy or a molecule on a very short time scale. Actually, it follows a Gaussian distribution. So what happens is the way in which it gets diffused also follows a Gaussian distribution, and it moves also in the opposite direction. So the opposite direction also follows a Gaussian distribution. So this is one property that is used in the diffusion models that is being used. So this is what we are trying to use as the basic property of diffusion models in machine learning. We'll see what is happening in machine learning, but you have a molecule, so you have this noise movement. So same way, if you have an image, you take a pixel, add some noise to it, and then you can follow the Gaussian distribution in the addition of noise, which we can be reversed at a later stage. So how this is useful for machine learning or how it is connected to our area. So in machine learning, if you see, this is a specific approach that I have just given the definition there. It's a specific approach for generating data using a stochastic process. So any stochastic process, which is like a Markov chain. So here what we do is that diffusion models can create new data samples. If you input a noise to it, it can generate new data samples. And so that is the main idea. So basically they are generative models. So it learns from a trained data. So we give data for it initially, we train it. And then, for example, if it's on the human faces, you can see that we train the model on human faces. And later, from the pure noise, we use the invertible operations, and then we can generate new kind of images or new data from it. So this is where how it is actually used. So here the key points are we need a training data set. Then we have we use a Gaussian distribution, and it basically comes into transforming noise into a structure. Okay, so the fundamental insight you can always note for a diffusion model is that we generate new samples starting from pure noise, and iteratively we remove noise through the learned transformation. Sometimes we can see that it was initially used for denoising. Suppose mostly the applications, when you look at it, when it is used as certain filters, or it is used in certain denoising applications also. So how any diffusion model works, there are many types of diffusion models, but how any diffusion model works is that these are the steps that are involved in building up a diffusion model. So first thing is they call it as a forward diffusion. Then we have a reverse diffusion. Before that, as usual, as like in any ML model that we built, we have to do some data pre-processing. So that is especially to ensure that, we have a proper scaling and centering of data. So we will usually, we say that we use Gaussian distribution. So a standard normalization. The standardization is applied to convert the data into a distribution, which I'm talking about the data pre-processing. Okay, so standard distribution with a mean of 0 and a variance of 1. So this is actually, why do we do this? This is preparing the data for subsequent transformations that during the diffusion process. So it will be easy to generate high quality images because we are standardizing the data. So that is mostly done in the data pre-processing. Why do we need this? Because then only the training becomes stable. Then we can add consistent noise to it, and it will facilitate gradient computation in a smooth way. So first, given we want to build a diffusion model, the first thing that we do is we have to pre-process the data. Second is always, where you would have heard about this, it's called as a forward diffusion. So forward diffusion is the model will start with a sample from a simple distribution. So it will be like a pure noise, as we say. Sorry, in the forward distribution, we have a set of images, and then we will begin with a sample from a Gaussian distribution, and we'll apply a sequence of invertible transformations. It's like, as I said, we are going to add noise little by little in a systematic way until, it's kind of, you are applying a sequence of invertible transformations to diffuse the sample. Okay, step by step until you will get a complex data point distribution. So this is meant by forward distribution. So if you have a image, then you add noise little in a strategic way. There are methods to add noise. And then finally, you will get a complex stage where it is fully it's only the noise that is visible to the system. So it's actually the forward diffusion process by adding noise to it. Then is the actual, where you can see here, we talk about the model training before the reverse diffusion. So actually we have this model training. Sometimes, we do the denoising. Here it is mentioned as score-based learning. It is not only score-based learning. This slide happens to be like that. There are any method that we can use for which we will be discussing. It could be either score-based, or it could be a, denoising probabilistic models that we use. Diffusion denoising process, DDPM, which is a very famous one, which you have heard about it. Any learning mechanism. Okay, and then we will train the model. But actually what happens here is that this training is, once we know that how we have added noise to the image, we are training the system to understand at each time step how much noise is added to it. That is the actual training that is happening. So your system, this model, when we talk about model, it could be an ML model. So it could be anything, any machine learning model. Mostly in the initial paper, they used a unit architecture here for training the model. This model will predict any time what is the actual image and what is the noise that are added into it. So for this, we actually train the model because we know the image in hand. We also know how much noise we have added to it. So for training, what we do is we are making the system efficient, okay, to predict how much noise is there at each time step. Sometimes it is also can be used for predicting how much information is there the other way also. So here, this is learning the parameters of this invertible transformation. As again, we know any loss function will be there for the model. So it becomes a normal regression problem, like you're going to optimize the loss function. And we can calculate either if it is score-based, we'll calculate the score function gradients, or it could be another probabilistic model. We can you make it as an optimization problem where optimize the loss function. Hello? Am I audible?
Yes, yeah.
Okay.
Audible.
Yeah.
Yes,
Okay.
yes.
So this is what we do So this is what we do in training the model. Okay. And then the fourth step is always reverse diffusion. Sometimes reverse diffusion is nothing but the whole process. After you train it, you are trying to start in the simple space, like you have a complete noise, apply inverse transformation, gradual refining, the whole process. At each step, you will do a denoising. I think we'll go detail into a particular problem, then you will understand. At each step, it's a set of denoising. Like at time t, it will denoise, it'll check with the actual image, how much noise is there. Then that is again passed through it, and then time t plus 1t. So it actually, if you have an image with x naught, it is transformed to xt. Then from xt to x naught transformation happens in this reverse diffusion stage. So it keeps denoising until it achieves the actual image. So it could be an actual image, or it could be a random image which is similar to the actual image, because it is just randomly generating it from the Gaussian space or from the Gaussian distribution. So it could also synthesize a new image. Okay, so this is the basics of diffusion models, whatever we use. So how we are going this, it may differ based on certain things which we will see. What are the other diffusion models? What different types of things happen with different approaches are there for here. So why this is, how come this is there? We have learned about other LLMs which can generate things. So first time people came out with this kind of model, like in DALI, if you can see, they wanted to generate images also. So typically our LLMs were used for text-based applications. Then people wanted to apply it for other mode of inputs, like, or other modes of data, like on a video generation, or image generation, or it could be image, like, style difference, like one image to another image. So these were some use cases that we wanted to solve. And then that time this model has come out, and there are a lot of benefits for this diffusion models. So we know the other methods like GANs are there. They are very good generative frameworks. Then we have variational autoencoders. Difference is that here the image quality that we talk about is actually is better. The image quality is, superior sample quality is there. I think I have slides on that. That is, if you see that there is a paper on OpenAI, that is what I have mentioned here. You can just go through and check. Then they came out, they were having a thorough evaluation of the diffusion models, and then they've given a paper which says diffusion models beat GANs on image synthesis. Okay, so they have demonstrated how it is actually improving the quality, because they generate high quality images with fine details and realistic textures. That's what is important here. Okay, so that is one advantage of this. And then second is there is a training stability. Okay, GAN has, we all know, it has certain drawbacks. There is always a trade-off or a delicate balance between this generative and the discriminator learning rates. So there can be a mode collapse that can happen if generator fails to capture all the aspects of data distribution. So here this advantage is that it's always looking at the likelihood-based training. Okay, so this, because of which it will ensure stability, and it avoids collapse totally here in this case. So that is one important advantage of using diffusion model. It has got this training stability, and it overcomes the mode collapse which was there in GAN. Another important is privacy preserving. Why we can call this as privacy preserving is that because this model is based on an invertible transformation. Sorry, why it is? It is built on an invertible transformation. So it uses kind of from the data, there is a transformation that takes place. So it is possible to generate the synthetic data samples. So sometimes this private information is not exposed as much as in other cases. So that is why they use them for healthcare applications. You can see DALI images. We have seen that it is used for generating like you give an X-ray image, you get a MRI image for the same case, where if you have trained it with both the data like that. So mostly it can be applications you can see with the DALI and other stable diffusion models with healthcare, or some sensitive applications areas where finance and other domains where you have a strict data confidentiality. Then comes the missing data can be handled easier. So sometimes when they have incomplete inputs during generation, diffusion actually, it can work well with incomplete samples, because even with the missing input data, it can actually can generate, coherent samples. So even when parts of the input data are missing, because it is generating from a space on it's from a Gaussian distribution or from a space where you can randomly generate a similar or a new image which is there. So that is another advantage. And there are other advantages too, like, one which is not mentioned in it. If you're noting down, you can just note it down. Like it is, it reduces overfitting. We know that GANs can be prone to overfitting. Okay, but here that does not have the because in model is not memorizing the training data as such. So it reduces this overfitting. We know that there is a latent space diffusion models, latent diffusion models, LDM. So they converge to they start from a latent space. So that is actually interpretable in the case of here, more interpretable than GANs. GANs also work with latent space, but still here it is more because this has additional variations every time and generate diverse samples. So that is another advantage. And then it can also be scalable to high dimensional data. We are not, that is not a restriction in the case of, like if there are larger resolutions, easily we know we have problems, we resize the images sometimes. But in the case of diffusion models, we can, even if the images have larger resolutions, we can actually use a diffusion model because it, efficiently it is just generating a complex data distribution and then it traces back. So that is also another advantage which we see. Applications, as all of us know, we have how many of you, I don't know, I'm not asking questions as such here, but many of you would have used any kind of already available pre-trained models, which we will see which are the most famous. But other important applications are like, for example, what is this in between? This is happening like 1 minute. Okay, so if you see one important application is text to video synthesis that all of us know. Okay, so text encoding, like if it will convert descriptions to encoding. Am I audible?
Yes, ma'am, you're audible.
Okay. So here we can see that, actually, if you given a text, it can actually generate a video. So text encoding is given as input, then forward diffusion generates frames step by step, then refinement takes place, reverse mapping. You can just have a case, look at Meta's make a video. If you have not seen earlier, how actually it is creating this coherent videos from the text, which is most famous here. Here it actually uses what is called as a conditional generation, which we will see how conditional generation works. Because of this conditional generation, it creates, visually compelling videos, very, very interesting videos that it can generate from the textual prompts. That is one case. Then image to image translation, that is another important thing. Here, what it does is that it will preserve the semantic information and the visual coherence. You can see image colorization, we have done style transfer. So we have been using this Ghibli art for a very long time. So we know there is a different style transfer application that happens here. Then image to sketch conversion or resolution enhancement, as we say, if you have a low resolution image, you want to enhance it to high resolution image. So that can be used. You can see that in 2020, this was the initial paper which came up with the influential DDPM paper, which we use it for image to image translation also. Applications are there. So that is another thing. Then we use it major for image search applications. So you can see even, there is a query and the database images are there. So you have a query, you have the database images, and then it can just pull out based on the content. So it usually supports the content-based retrieval. So if it is in a latent space, what it does is that it will just calculate the Euclidean distance between the query that you have given and the database images, and then it pulls out what is there. It can generate, it's mostly, this example which I've taken is from Encode. What they have used is that if you can log into Encode and see, choose a project, use a natural language or image similarity, any option that you can give here, that is what is given there. If you give that, it can generate logo templates on its own. Sometimes it is useful for other things like creating image libraries or image databases. You can generate and keep an image database, or sometimes in the reverse image search engines also, these applications are used much. So generally, if you see, this is how it works. The example which people have in the encode, this is the option that which I just now explained. What they do is that they are mapping images to a simple distribution via reverse diffusion. Then they use this query processing, and then after uh, getting it into a latent encoding, they use the query processing, and then they check for the similar images with a simple distance metrics like a Euclidean distance, and then it is retrieved. So this is how it is used for an image retrieval. So then that is it. Now we are talking about all this. There are different applications that are there. Okay, so then how do we know what are the, so this I just checked, I have asked, I think not ChatGPT. I was just confused while looking at it. There are different models of diffusion model. Is there a proper category for diffusion model? So that confusion was there. And then what I understand from here is that, see, this is how these diffusion models are categorized. So I have told you what is a basic way in which, or what is a basic mechanism in which the diffusion models work. So, but it can be categorized based on certain criteria. So if you look at the mathematical formulation of different diffusion models, there are different types of diffusion models. So in the paper initial paper 2020, which we just referred earlier, that was using a DDPM. Slide is not visible. Huh? Now?
Yes, ma'am, it's visible.
Okay. I just got a message. I thought somebody said it's not visible. Okay. So based on the mathematical formulation, DDPM, that is, or score-based functions, or it could be ODE, SD, differential equation models. Then there are different categories of diffusion models. Suppose you are looking at the data representation. So like very important, the initial model was based on pixel space diffusion. That is, it worked or added noise into each pixel in the image. Then it becomes a pixel space diffusion. Then came with a very famous, because it is very complex and time consuming. Then people have come out with an idea where you can, apply a diffusion model in the latent space. So that is called as a latent diffusion. So you can use any encoder to get in a latent space, and then we can apply the diffusion model there. Stable diffusion is one example of latent diffusion models. So that is this way also you can categorize diffusion models. Then conditional or controlled diffusion models. So initially they have come up with a naive model where they just did not add condition as such. It was working on the random noise, but you can also add conditions to it. If there are no conditions, they are unconditional diffusion models. If you are adding conditions to it, then they are called as conditional diffusion models. In conditional diffusion models, sometimes you can add text or labels or any vector which you can, it could be a context also, which can be added as a vector additional to the to the input, that is in the training process. Then it becomes a conditional diffusion model. There also you can have classifier based guidance that can be given, or classifier free guidance. You can use any classifier that actually adds overhead to it. When you add a classifier to the diffusion model, it actually enhances the model, but the model takes little more time because of the overhead of the classification model. So either you can go for a classifier free guidance or classifier based guidance. There are few models like that. Then if you look at the output type, image to image or audio to image or audio to video, those kind of, that also some pre-trained models are there.
Ma'am, your mic is mute.
Sorry, now?
Okay, okay.
Okay, so now what we do is that another very important model is, so you should not, if you just look at any paper or if you look at a pre-trained model, just read initially what is the basic training mechanism it is using, what is the data representation it is using, are they adding any condition to it, what is the input given and what is the output that we take in, what is the sampling method. So there can be a combination of all this. For example, if I look at a say classifier free guidance, I may be using DDPM as my, or score based method as my for the training. For the training, I may be using a probabilistic method or score based method or a differential equation method. So we have to, it's a combination of all this. Finally, some diffusion models, we know that what is it used for, whether it is a denoising diffusion model, then it is going to predict a noise, then it can be a denoising diffusion model. Sometimes going to predict the data also, because we know we also keep at every step it also understand what is the actual information. So that also can be another objective of training the model, or it will be a velocity prediction, or it could be a new data prediction, image any synthesis or new image, new data generation also. So these are the different categories which I was just made this and given to you. So based on this, if you can pick up anything, you can check what are the different models, that ways in which it represents, and that is how the different diffusion models are created. Now we will see the what is the next one? Well-known diffusion models are there. There are many diffusion models that are available. So if you look at it, we will just see one or two. The base concept is same, though they use, as I said, they will be using different techniques for building this model. So the first and most important is, or the initial paper was on DDPM model. Okay, so as we all know, I've already told you what is the whole concept. You have a forward process, you have a training phase, and then we have a reverse process. So let us see how this DDPM, which is basically working on a variational inference. Okay, so how this actually works, let us just see. So here what happens is we are using a probabilistic model. So forward process, okay, forward process, we are going to add the noise. In the training process, we are going to predict noises at each time step, and then we will use this to clean up the data. Then we just have a continuous denoising process that takes place. Then in the reverse process, we are going to generate new samples by starting with random noise. So that will be like a trained model, which we are going to, model is trained, and then at the reverse process, it's like an inference that is given to the model. So this is how, this is just another slide. We'll go to the example. So you can see this is how it works. Suppose you have, this is the initial image X0. Okay, and it consists of two processes, forward diffusion process that you can see. We at each time step t, we add in a, at each time step t, we add a little bit of noise to the original image. So X1 is more noisy than X0, X2 is more noisy than X1, and then we continue this process until we get only noise. So X0 to XT is mostly, it is using any kind of a stochastic process like the Markov chain to add the noise to it. So XT is in the reverse process. What we do is that we have a training model to understand how much noise is added at each time steps. The model actually learns the noise, or it learns the pattern at each time step. What is the original data and what is the noise? And finally, you have in the reverse process, you will do the opposite of this. We will be denoising it a little by little, because we know how the noise is added. We have trained the model which understands how much noise is added. So then from XT to X0, there is another retransformation that is happening. So if you look at XT minus 1, it is less noisy than XT. And then given an XT, it generates either X0 or something similar to X0. So this is the base in which it works. So if you look at the mathematical part, as we know, we are just So here what we are doing here is that, but in this equation, you can see that we are actually q of xt given x naught. That is, we are going to generate, this is the forward pass. So we have an initial image x naught, which is given to us. We are going to convert it into an xt by just applying a, we are going to apply noise. So you can see that this is a normal distribution. We are just going to pull out. So here, if you see, they are actually in this particular equation, they are just giving you that it starts from a simple distribution and gradually it is, it is diffusing to the full noise. But in general case, you can see here, it takes a x naught, corrupt it with an oil until pure noise. But noise is added step by step manually, which may take little time. So in this case, what they have given is that they are jumping directly to xt. That is how we have done that. But in the real case, when they started, when they it was initially done, it was added little by little. Okay, with like a example of a Markovian chain. So here noise also, if you see, alpha t represents the actual information that is there, and beta will represent the actual noise. Beta is equal to 1 minus alpha t. So this we know it's a sampling from a space, it's a normal distribution where we have, this is the mean and this is the variance. So normal distribution with a mean and a variance. So this is how this transformation takes place from, always is between the values 0 and 1. And if you see, it follows a schedule for adding this noise. It has a value, that is how much noise is to be added at each time step. So usually that is called as a schedule. That is, the first paper had a linear schedule that was used, where they just pulled out the value for alpha initially was 0.0001, and then it up to 0.02 was the value that they use for adding this noise to the thing. So then they understood that the linear scheduling takes a lot of time and lot of iterations are there. Then consecutive papers came up with other noise schedules. So they used a cosine noise schedule for adding noise to it. So either you can look at the alpha t, which is the actual information gain here, or beta is equal to 1 minus alpha, as we know, which is actually the noise in it. So the model is, when we add, it is added little by little. In the reverse process, we can either the learning, we will just see, it will actually learn what is the actual data that is there as well as the noise that is there. So here we know, then what happens is that, so this is, if you look at the generative model that we are using for the reverse process. So in the forward process, what do? We had a known distribution. So we had q of x, like given xt minus 1, we can get xt. Okay, so if you give me xt minus 1, we can get xt. That was our forward process. Now we are going to hear what they do in the reverse process. It's just the opposite of this. So they are giving you p of xt minus 1. You give xt, we get p of xt minus 1. So this is actually an unknown one, but that is why we are using a neural network to approximate it. So generally we can see it becomes a neural network which can actually do the approximation. And then theta is the parameters that we are using it, which the neural network actually learns. Okay, so the key idea here is that we know that each reverse step also actually follows a Gaussian distribution. So what do we want to, we know that the mean is going to be 0 and the variance is going to be 1. So we are going to predict the mean learned by the model. So every time the model has learned the mean, we are going to predict what is the mean that was learned by the model. Okay, and the variance is fixed, or it can be, often it's fixed or predefined. Hence, only the mean that it is going to learn. So then it becomes like, the model, whatever is the neural network that we're using, mostly it is the unit that is used. It is just trained to predict the mean of this Gaussian. So we can see that, the general, instead of looking at this, we can say, how do we do this full join, or what is the objective is that each reverse step, we are going to model as a probability distribution. So you have given a noisy image at step t. we predict the distribution at step t minus 1. Okay, mean predicted by the neural network. Entire reverse process can be, this entire thing we can reverse process, we can, if you look at the learning objective, denoising matching term, finally, this can be like a product of the transitions that takes place from P of xt in the distribution of normal distribution n of 0, I. That is with the mean of 0 and variance. Variance is going to be mostly fixed. Okay, so this is how it generates the value. And in this equation, we can understand that if we know this with the KL divergence, this has again, this term would be very familiar to us because this has become a regression problem here. So training is nothing but that is why we are using a deep neural network or any neural network, because it's very good at UNet is mostly used because it's very good for image to image tasks, because it can, you give a noise image, you can predict the noise because it is good at the regression problems. So your sample is from x0, you give a noise of eta and time steps t, 3 values, and then you train the model to predict the eta at each step. So entire probabilistic model, it works on a simple loss function. If it is the case of a score-based function, then it will learn the score values. You will be mapping it into you have a score function, and then we'll be mapping it into a score value, which you will calculate the score value with instead of the noise, we'll be look at the score value. So actually, inherently, the score value and the noise is similar. So that is what is used in the case of a score-based functions. So here, so now what happens is, we understand that the reverse process becomes like a simple regression problem with all these, and the neural network becomes, it is a probabilistic model where it has to find out the simple your MSE loss. So what do we use for this? What is a network that can be used is, and they have used a UNet, and there are other variations, but UNet was initially used because it was an established model, and this is where there is a condition given to it, but we'll come back to that later. But if you look at it, we know that UNet architecture, we have encoder. There is actually we use an encoder which can compress the image. We have a decoder which will reconstruct the image. So this is just an example we have given. Initially, it is a denoising, that is a reverse process starts with it, and then it learns. It iteratively the loss is calculated, and then it predicts the noise at each time step, checks with the actual image, and the error is the difference is calculated between the actual and the noise, that the predicted noise, that is again passed through the network, and then it keeps learning until you get an actual image. So this is it. And then this is what we just said: original image, then random uniformly sample Gaussian noise, and this model predicts each noise at time step t, and then the loss is the same usual training that we all know. So we are using an optimizer there, and then it calculates the loss, and then it works on it. Okay, so these are the applications of DDPM. As we know, this was the initial one which was there, and there are many all these applications we can use with DDPMs also. And see, we have an okay, so image denoising, it can be used because it works as a denoising application, and image in-painting or super resolution, all these applications can be used with DDPM. So this is the most famous one, initial one. Then actually DDIM also has come in, which we will also discuss. There are many methods that are there. The second one could be which was more famous, was similarly we have just used a score function. So instead of that was a probability. You used a probability, DDPM had a probabilistic model. Here it uses a score-based generative model. That means it is going to have a score function which is defined. So if you just look at a score function, it is the gradient of the log probability density. So we know that it is going to predict not the exact point on a normal distribution, but it is going to predict the density, probability density of it. That's why the equations you can see here, this represents the density. So it will explain to you which direction you can see delta x log p of x, which is actually a probability density, or the delta x is the gradient value of the probability density. That is, so we define a score function which will give you the score value. So based on the score value, we will know which direction to increases the probability of reaching the actual image. So this is what is used here, and the probability estimation is also by integrating the score function. So based on this, it will check on a point on the data space. It calculates it instead of error. It looks at what is the value of the score function, because this is actually a gradient of the probability density, and it tells us which point has high density regions. So based on that, this learns. Same way, training approach is same. What we do is, if you're following the score, we will be just following the score, which will move forward regions where data is more likely. It's like, the simple, which we have learned, like hill climbing. Climbing, the gradient tells us which way is up. So what is the criteria that we use here is that, I'm not going into the exact maths of this, but we don't know the true probability distribution. So we learn its score. Instead of the probability distribution, it is learning the score. So delta x log p of x is done directly. We are not computing the p of x as such. But here, what is calculated is the delta x. What is the gradient is calculated at each step based on the score value that is calculated out of the score function. So you can see that here, again, we are training the model with noisy data, as we saw here. I'll come to what is Langevin dynamics. But before that, I think I've explained this. We train the model using same thing, noisy data, noise to data, train the model to predict the score of the noisy data each time. This is the method is, because it's a diffusion model, it is the same as that. Same method it follows. So then there is there is one in a score-based model. They talk about what is a hello.
Yes, ma'am. Okay, continue.
I thought somebody asked. Okay. So there is a concept that is used here is that what is the what actually helps you to move, though we have this value, looking at the delta value, we can understand, or it is used to climb the hill or move towards the high density area, but still it follows what is called as a Langevin dynamics. That is first term of this. If you look at it, it is helped with our xi is the actual value, plus we have calculated the delta here. So this first term moves towards higher probability, and the second term helps you to move towards randomness. I just forgot to tell you one concept here when I just looked at this. In the actual DDPM models, when we are working with it, with that also, when we, in the reverse process, we actually add a small amount of noise at each time step. We'll come back to that, at least the demo which I tell you. It actually predicts the noise. Then we also add a random noise to it, because we wanted to explore more regions in the distribution space. So because otherwise, if you're not adding more noise, it may not, it may become stable at one point, and then it may not generate the actual images. So it could be in a paper they have mentioned that when we are adding a random noise to it, it can actually generate better results. So that I just forgot, because otherwise what will happen is that because it is randomly generating and it becomes a fixed learning. But if you're going to add certain bit of noise to it on our own, which could be a very meager value, but then it will be helpful for, like in the case of RL, we use this exploration exploitation concept. Similarly, here this noise can help us to actually move around the space and explore, getting a better results for it. So here also the same concept applies here. The first term is generally, this is how it moves, helps you, or it drives the algorithm. That is, it moves towards higher probability. But here we are adding a term which can add a little bit of randomness to it. Otherwise, we may get it could be on a plateau. So instead of that, it gives you a balance of gradient descent as well as the noise. So this is called as Langevin dynamics. and this was proposed in this model. So score catching is done. A noise is added little bit, and the training happens. So here actually what is the connection to diffusion is that if you see this is how they have used an MNIST, and in this paper they have come out with MNIST, LLM, differ and all that. Diffusion learns noise, whereas in score models what is learned is the gradient. Okay, both are equivalent, but they're the same process where we learn the noise prediction using DDPM models. Here we are just, instead of noise prediction, it is estimating a score. So your network will estimate the score instead of predicting the noise. Then another method is, there are many methods, as I'm not going very detailed into it. So I think the previous one is somewhat clear, because there are variations of DDPMs, as we saw in the first slide. There are different types which are there. So here this is discrete denoising process is done. Whereas in the conditional diffusion with classifier guidance is another area. This is very important. There is something called as a conditional diffusion. So instead of generating any image that we did, now we are going to guide the model. There it was a unconditional in the initial work, initial proposed model. But then people understand that to get more accurate result, they introduced conditions into the diffusion model. That is called as a conditional diffusion. So instead of generating, we may guide the model to generate a specific type of image. Okay, so here also, as I said, it could be with classifier guidance, or it could be without a classifier also. There are many conditional diffusion methods. So like, for example, generate a cat, you give a cat image. Also, this condition can be given as a text or a vector, any embedding that can be added to it, or there can be a classifier which helps to classify at each step, okay, which is an overhead to the function, or it can be an additional information given to it other than the image, plus you add the noise. It also enhances the ability to learn a pattern by giving a condition to it. So in the case of stable diffusion, it is a text, like they use a clip kind of a method, the text encoder, and then they add a text encoder also. Sometimes contextual meaning is given to it. A concept can be added to it, or a text can be added to it, or it can be timestamps, additional timestamps that can be added to it. It'd be like, you give a cat image. Wait, let me see what is the next one. This is with a classifier guidance, but I want to tell you the general thing. If you, instead of giving only a cat image, we can give a cat image and say, generate a cat, generate a dog. Or it could be generate an image from the text prompts. Mostly text can be, or text prompts can be used as a condition also. So initially, instead of like we wanted it to predict P of X only, we can model it as P of X, X given Y, where Y could be a condition. Okay, that slide is missing here. Then it could be general in the case of a condition diffusion. So it will be condition can be, that is P of X given Y. Y could be a condition. Condition can be a label. It can be a text, as we said, or there can be a classifier who will help us to classify whether it is, we are in the right direction or not. So in that case, we have to explicitly build a classifier guidance. So classifier guidance is that, so this we will come to that. We need to train a classifier on the noised data again. So here, what we have to do, we have to use a separate classifier that will guide generation towards a desired class. We can fix it up. So this was initially done, but it takes it gives more accurate results, but it takes more time, because we are going to have a gradient. We are going to use the gradient from the classifier. As we said earlier, if you are using the delta X, would be calculating the gradient from a classifier also, rather than the noise that we calculated and added to it. Instead of that, you will use a classifier to say whether it is a desired class or not. And then the gradient of the classifier is used for your diffusion process, reverse process, training process. So during sampling itself, the sampling is nothing but the reverse diffusion process, the training process. You predict the noise. What the general diffusion models, we know that we predict the noise. That along with the noise, you can add a classifier gradient also. Okay, so this was introduced in a paper. So this is one type of a, just one type of a conditional diffusion model. So we know brown hose class, for example, this could be any classifier that we build. And then we have already given that brown hose classifier. This is the decision boundary. If you wanted to generate a brown hose, this classifier will predict whether it is a brown. So you know the prediction value. That classifier gradient can be added in the learning process. So other than the noise, the classifier will decide. And so it's like if we are giving a manual information to it, other than it learns, there is somebody to help the process to learn better or accurate. That is important. So this is what I just told you. You denoise it, you add noise, and then you have a guided noise added to it. This guided noise can be in any form. In the case of using a classifier based one, it could be the gradient of the classifier. So the paper you can see in 2021, they have come out with this. And then they said when we are using a conditional model, it is generating more accurate results. And that is what was explained here. In the case of a classifier free guidance, it's a modern standard actually, a joint conditional unconditional diffusion model here. So it could be remove the classifier and let the diffusion model learn conditioning directly. So we are going to embed this condition as an addition. We are not going to have a classifier to evaluate it and then give the gradient, but we can add condition in the training phase itself. We'll come to that. Okay, by concatenating to the input. So as we said, we will also give a semantic information. Say, for example, we can give a text to it. We can give a prompt to it. I think there is an example here. Oh, no. Okay, so I had that example. Like, for example, I don't know where. See, one, it could be like, avocado, that text is, that semantic meaning is stored in there. Then you have a different chair that is being trained, and then we label it. We give the label sometimes. We sometimes give text to it. We can add any additional information that has to be memorized, which is used for synthesizing new image, can be added as input or like a cross attention also. So if you look at stable diffusion, it uses in the latent space, it actually uses a cross attention. So it will learn from which part of the input or from the noise that is, that is captured, what part contributes to what, which area of the image. So that is, we know what is, I think you would have learned all the attention mechanisms. So stable diffusion uses a cross attention here for the conditioning of the entire model. So that is called as classifier free. So you can train classifier free guidance, as we said, with condition Y, or without condition. Sometimes randomly we can drop the condition during the training also. That is also possible. There are many methods that are available with the classifier. We have a example. I will demonstrate how conditions can be added to it. So this is increasing guidance. So this can be added at any point in the training phase also, where you want to embed this vector at times t, which time step you want to embed this condition to the training process. That is also possible. Then this we will skip. There is another important type of method which is called as SDE, that is based on the stochastic differential equation. So this is now that I will just skip for now. This is one comparison which I wanted to, when to use which type of a model, but there are more papers on that you can see there. So if you have discrete time diffusion, the basic thing, the DDPM can be used. Suppose you have a probability density modeling and then sample generation, then you can actually go for SGMs that we have not seen. SDEs are used for continuous time frame based methods. So now, very important is a latent diffusion model that is mostly used nowadays, because if you are going to this, I think, do you remember what we said? It depends on diffusion models working on either pixel based or it works on the latent space. So if it is pixel based, we know it depends. When you add noise to each pixel, it takes a lot more time. So this as a breakthrough which has come in NeurIPS, you can see that this is a breakthrough which has come in. So here what people do is, this is a latent diffusion model, instead of running diffusion on raw images, that's what I said, pixel-based images, we can run it on a compressed latent space, because we know what a latent space is, just a representation of the original image, or it learns the entire distribution, data distribution. So they have developed, they say that the diffusion model can run on this compressed latent space. So then instead of giving X of image, we can use Z of the latent representation directly. And then we can we can use any, mostly any encoder, we know encoder decoder that I think you have gone through. So you can use any encoder, and then we can get in the latent space, which is a compression and lower resolution, and you can run a diffusion with the same, any diffusion model that we have discussed so far, that can be run out. So you can see here, what they're doing is encoder is there, you have a latent space Z, that's what I said, and there we are running the diffusion model. Okay, and then this at this low, see, this is the whole diffusion model that is being generated. So latent embedding distribution model with, so it is actually learning the distribution from the latent embedding, and then the diffusion process works. Then it goes to the decoder and discriminator. So that was introduced as the latent diffusion models. So we know images are large size, even if it's a 512 cross 3, very slow and expensive it is. So if that is why they have come up with solutions. It's a very good idea. So you compress the image, run diffusion, and then you can decode back. This is what I mentioned earlier. This is one advantage of diffusion model also. You can just get an interpretable latent space there. Okay, because latent variables into, we are taking that and we apply the reverse diffusion into that latent variables. So what are we can easily identify, it is kind of an interpretability brought into here, where you can find out which are the essential features and patterns that are used. So that is it. Stable diffusion, as we said, is a latent, this is one model which actually uses this latent diffusion model. Okay, so these are it's built by it, the architecture of it is like this. You have a autoencoder training, it uses an autoencoder, and then it uses LDM training. Okay, and then the applications we know in, say, I think you would have, those who are working in this area would have used, I think I have the architecture for it. Yeah, you can just see, this is the architecture of the stable diffusion. I just wanted to mention only on stable diffusion because it's kind of becoming a very default, in the latent distribution model. A stable distribution is it has become very prominent, and it is like how we say when we're talking about transformers, we talk about GPT, same way it is. So these are the components. It is also kind of, it uses LLMs here, because if you look at the architecture, this you can see, this is for the pre-training. What it is doing is, okay, the three main components are there here. So the first thing is the text that you give. It's a conditional diffusion model, because for the pre-training, what it does is that it uses T5 or clip. So it looks at, it actually creates a embedding that is a massive text to image pairs for semantic understanding is done. This is I told you in the beginning, that is all this diffusion model follows this, but in this case what they have done is they have used a clip, a contrastive learning method. I think you know about clip also. It is where you can say large language models are used for diffusion models. So that is used, and the text is encoded into embeddings. Okay, that is one advantage. So it becomes a conditioned diffusion model. Okay, it is not using a classifier, so it's easier now. Number two, the flow is, it is represented in latent space, so it is not on the raw pixels. Then diffusion happens in the latent space. From latent, it decoded back into the image. So what will happen if you are giving because you are using a clip, it understands the prompt. Okay, the prompt is understood and then it is converted into embedding value, which is used at the time of training. So this becomes a conditioning signal. That is the most important. They have used all the advanced logic here. So this, if you, for example, like we say, like what to say, a very beautiful sunset or a city with a sunset, that is the prompt that we are giving. The vector representation of it is, that is the semantic meaning is calculated. That is why I said it uses clip here. And then that is added as an additional embedding to it. Okay, for giving a conditional signaling or conditioning signal is the embedded vector that we have given. So it's trained that way. So it's a conditional diffusion model. Then it uses the second architecture. If you look at it, the encoder, they are as mentioned here, they are using a variational autoencoder. So we know encoder for image to latent space, and then from decoder from the latent space to image is done. So what is the purpose here? If you're giving a 512, it makes the diffusion faster and cheaper. Then as typical for the training, again here, the third step, it uses the unit only. So we know this is the, for unit is the, it's used in the sampling or the training part. So I've already explained how unit actually works. For your training, it's a typical which learns to predict the noise, but along with this, the conditions are given. So like if you look at it, downsampling at the time we saw the unit. So at the downsampling path, it will extract the features and spatial size is reduced. Then upsampling, it reconstructs the images. So here it uses also skip connections to preserve the fine details. Very important in stable diffusion is, if you can say, you know, what made it so accurate is, first thing is the pre-training, it uses the clip, then it works on the latent space. Third is it uses unit, and it also uses a cross attention here that is added to it. So how it is made as conditional is because, say, it uses the, like, for example, if you say which part of the image should attend to which words, that is understood by using a cross attention method in the case of a stable diffusion. So image features, we give it as queries. Text embeddings are given along with it. The keys and values are given. It learns that also, keys and values. So you will know, like for example, as I said, it learns a set of avocado images. It learns a set of, say, chair images. Suppose I give me a model of a chair with a chair which looks like an avocado. So it can generate an image learning the features from avocado because it knows what to take from avocado. Then it can learn from what are the important features at with the chair, and then it generates an image which is very similar to looks like an avocado chair. You know, I've not got that example here, or anything like that. So that is the important because you are giving a conditional diffusion here. This is how it learns from the. So this is one exam. This is one. And we are not going to. Other important model is like stable diffusion. We have this DALI. I think all of you have heard about DALI. That also again it is using this same. Some I have not got the architecture here much, but you can see again it is using clip. If you have not gone through this contrastive language image pre-training, kindly just you can see what it is already. It is already a model, pre-trained model, which is pre-training things. It's called as contrastive language image pre-training, which is given by OpenAI. I think you have used it for certain research work also. That learns to connect images and text. So in the it's actually giving a semantic meaning to it. So that is what is used there, as well as in DALI-E also. They use the same method. Then another important pre-trained model, I don't know who has developed this. I was just checking in the internet. Imagen for deep language understanding, they have used similar diffusion model is there. Glide is another language to image diffusion model. So that also is there. You can see that 3.5 million parameters are used in here. So these are some, I just took all these important pre-built or most famous, diffusion models. Earlier, what we mentioned was the concept behind it, the base architecture, but here they are all implemented models. For example, stable diffusion is a kind of a latent diffusion model. So that has different, as we said, the different components are replaced with the most optimal ones. So people are still coming up with a lot of, I was even checking for the sake of research, because one of my student was doing a research on this underwater sonar images. So we had a lot of issue with getting, to actually generate images. We don't get enough underwater sonar images. So we had a data shortage. So we wanted to generate this underwater sonar images, but then I think it's, I was just checking. I even asked chat GPT about this. Can we, they say there is a scope for research in that. Can we give different types of noise? We know that if it is an underwater sonar image, what are the different types of noise that is there? Not always is it speckle noise, or is it because of the water, the distortion that takes place? So can we use that as the, to generate an image where the noise belongs to a specific category? So I think I said that there is a scope for research in that, and that can be added in there also. But we are using something like a normal distribution, which is easier for us because it is predictable and it's easy for us to, it's a stable one. So, but is it possible to add in our own noise and then take specific kind of images, and then how do we use this diffusion models to generate a specific type of, a specific type of noises can be added, and can we generate images like that? So those kind of things, maybe you can learn a little more into it and understand how actually it works. So with this paper, they have compared all the 4 famous diffusion models, and then they have given some performance evaluation metrics also. So I'll just go, take you through a code that is already there. I have gone to Hugging Face, also has a lot of models, diffusion models, and different examples that are there. But this I took from OpenAI. I think I will just, this is one example which I will just show you a code that I don't know if it's executed now. One second. Yeah, it is somewhat executed. I just kept it. Now you can, what we will just see is in one example. There are many available in GitHub also. So this one use case which I wanted to, I in fact executed and saw was just to implement the DDPM model. Okay, we want this neural network to, have you heard about the sprite images? So we can download the sprite images. The link is also given there at the end in the notebook page, which I have just gone through. So they want to generate new sprite images. Okay, so what they have done is they've added, they are using a DDPM model, and they've added noise to it. Now, what is expected from the model is that the model should understand the fine details, generate outlines. Fine details means like what is the hair color. Say, for example, there are different sprite images like they're calling it as Bob, and then Fred, and so on. So fine details would be what is the hair color of it for it, and then what are the accessories that they have. General structure could be whether it is a sprite or not, like shape of the head and body, like that. So that is what is expected by the neural network to learn. So here also they are using a unit only. So it learns noise at different levels. So clear image is low noise. Okay, so this is Bob. It exactly says this is Bob. That's what they say. If it's a Bob sprite, keep Bob as. So if it's a moderate noise, it says probably Bob. Likely features and refine them. If it's a high noise, it will suggest general structure at least. This is likely a sprite, at least it can say, whether it is not specific to Bob or Fred. Or pure noise, then this could be a sprite. No likely, but this could be a sprite which is a pure noise. Generate a basic possible structure can be generated. So if you're asking it for no idea, like full noise is no idea, or you can say may be a possible structure for Bob. So what is our training objective? As we have seen, this is a noising process. We will see, as we said, they are just taken some so initial image was this, and that at time step 59, this much noise is added to it, and at 179, more noise is added. So I think it's 500 step, they add the noise. It's a forward pass or forward diffusion process, or the diffusion process. Then they are training a neural network. So the training objective, again, what is the objective of the training here? Is they're using a new, what's the UNet? So initially input is noisy image is given to it. Output is the predicted noise. Actually, okay, the predicted noise. The goal is to remove noise step by step to recover the image. So why do we use Gaussian noise? As I told you, most of it is, there are, you can also use uniform distribution and so on, but Gaussian distribution has been used from the beginning, okay, because that is for generating new images from scratch. Also, we are using this Gaussian noise only because it is very, is, very stable, and we know it is used for several applications because of the properties. So this is the sampling. Sampling is nothing but number of denoising steps. Sometimes people get confused with these terms, like what is a sampling here or what is denoising. At every time step, denoising happens. The entire process is called as the sampling. So here, what it starts with a noise sample, pass it through the trained network, and then it predicts the noise. So the actual image minus the predicted noise, you get the error that is fed back into the neural network, and then it until it gives you the actual image. So this is how the reverse diffusion takes place. So there are some, so unit architecture used here in this example is this input layer. So we will just see how this works. So implementation, they have used it on a PyTorch, and 500 time steps they have used. Image size for the sprite, which is given as 16 cross 16. Okay, so this is what another version of it is there. We will see they are adding to the unit. They are adding some conditions, as we just saw. Okay, so it is given more embeddings. We are just adding it only. We are not using a classifier here. They are giving a time embedding, which is related to time steps and noise level. At each time step, what is the noise level? That embedding is added to it. And then they are also adding another context embedding vector. So text description is added here. So here the condition is given in the form of a text description. Okay, so you can see that in the code, they are just adding this context embedding as well as time embedding to make it as a conditional diffusion model. And the training is done. And I think, as I told you, when at each time step as a noise sample, you have to add a noise back also. Okay, so otherwise, we want it to see, why do we add an additional noise at each step? Is that the model is actually trained to pick up a sample from the actual, properly distributed sample. But what happens is, when we are training it more accurately, removing the noise and giving it the image with lesser noise, it is actually trained for a properly distributed. Okay, so what will happen? If it is no longer properly distributed, then it's not normal noise anymore. So the system may not be able to perform better as expected or as it was trained. So as I already said, in order to keep some exploration, we have to add add in a small noise also. If you don't add the small noise, the outputs becomes blurry. So that also in the code it is explained why the outputs becomes blurry. So because of that, a small noise is added into it. So these are examples of the embeddings that are given there after we do, as I told you. So this is for controlling the model. I told you what are the different embeddings that are there. Brownian, for example, Brownians often bump into each other. This is embedding, then what is an embedding vector? This is also added in the unit as an additional thing. So this is, sometimes, you can also given other contexts, like either through the text embeddings, or it can be instead of the classifier and then using a classifier and then using the gradient of the classifier, instead of that, we can directly give categorical vectors also. Like when you give in an image, you can say this is a hero or non-hero. So if it's going to be specific, if you want to fine tune the model, no, for a specific, like you use RAG in the other cases. Similarly, here if you want to fine tune the model, you can make it more specific by giving categorical vectors also. Like if it's food items, apple or orange, whether they are apple or if it is orange, by giving some labels to it, spells, orientation, something like that. That also can be given as context. Okay, so that is what is done. Now, as for speeding, so this is this is the example that they have used in here. This is what I told you. So here you can see, because the context is added. See, you have a ripe avocado. So this is the this is the text that is given to this the training image, like a ripe avocado. And then we have a set of armchair. We say comfy armchair. Instead of it learning without condition, we can also train it using these samples, using these meanings. It's kind of giving a contextual value to it. So we will be giving this. Then in the sampling, this is done in the training. Okay. During the training, you do like this. In the sampling, if you give avocado armchair and give it can sample it, it can bring in something like this, because it knows what information is to be fetched from both, what is important. So that's why I said in the case of stable diffusion, it uses a multi-attention. So when you give an avocado armchair, it knows what features corresponds to avocado and what features corresponds to armchair. So it is trying to build something, mixing up both the properties of a chair as well as an avocado, and an image like this is synthesized. So if you can try the same code without giving a text embedding, okay, without adding this context, you can, if you train it, it will still generate something, but it may not be that accurate as what we expected here. That's the importance of condition. So this is an example of how a context vector actually works and all that. Then last one more concept in this is that there is something called as DDIM. I have just pasted the screenshot. I don't know if it's clear. As we said, there is something called as denoising diffusion. Implicit models are also there. Okay, it's a paper name. They have come out with one kind of a sampler, which is quite faster than the DDPM. Because there we know for sampling it, each steps is depending on the previous. I told you in the beginning, it is using a Markovian process. It's stochastic process, especially Markovian process, because at each time step, we use a schedule. What is used to add the noise? We have schedules. It's called as a schedule, and different types of like a linear schedule, or we have seen cosine, that is used to add noise at each step, but it's following a Markovian, and it takes many time steps to actually converge to become a pure noise. So then for a faster sampling method, they have come out with something called as DDIM. There are many in this area like this, but one I just wanted to tell you, they skip certain time steps. Okay, so this is breaking the Markovian assumption. It is just removing randomness again, but it becomes deterministic. So that's why it's called as implicit models, denoising diffusion. You remember in the beginning, in the categories, I have just mentioned that we have continuous probabilistic models, as well as we can have deterministic models also. So that was introduced in this paper, and found that this was 10 times faster than the original DDPM work also. So in DDPM, they tried this use case, which we are going to the code which I'm just going to fastly walk through, has this DDIM implementation also. And we can see how faster it actually converges. There it was 500 steps, and here they skipped it to adding not on a probabilistic model. So added noise in a deterministic way, and around 20 steps, it's kind of there. It was 500 steps. It is around 20 steps. Sometimes it is, but there is a quality trade-off, definitely. That also is mentioned in the paper. Okay. Though it is faster, it is good for fewer steps, but quality compromise happens sometimes when we are using DDIM models also. But speed improvement is obviously there. So these are now let's just go through so this is an example of how DDIMs are faster. Okay, so I will just take you to the code, how the implement. You can go to Kaggle or your GitHub, a lot of repositories or Hugging Face, and you can check how it works. So I will just. We have tried that here. It was taking a lot of time. So if you have to use the GPU, so I've used to a T4 connect, and then this we have just executed at my run Google Drive. Let me check if it works there. We'll wait for it. But before that, this is what I just explained to you. What are the different components? So nowadays, we don't write code as such, but you can see these are they are using a PyTorch. And this is where their unit is constructed. And we embed the time step and context labels in one layer fully connected neural network as that we embedded. Okay, and context embedding is also done. And then, as we said, alpha, beta is the noise level. In the first slide, we just mentioned alpha is equal to 1 minus beta, beta is equal to 1 minus alpha. So beta is the noise value that we are giving into us. So here they are following a linear schedule only. And it starts with in the paper. This is just an implementation of the initial paper. Slight modifications are given. So 0.001. They have used starting, and beta 2, it reaches up to 0.02 in the final at 500 time steps. And torch device, and then the images are 16 cross image, 16 cross 16. So this is how the DDPM noise schedule, which I just told you now, is used here. So this is the equation. Actually, you get the beta 2. This you can see beta 2 minus beta 1. If you can calculate, beta 2 is 0.02 minus 0.001 and divided by the number of time steps. Okay, that is how much to increment at each step, that is given by this equation, because it's a linear schedule. You can plot and see the values. It is actually incrementing linearly. Then the model unit is constructed. This is the sampling, that is denoising, number of denoising steps. Okay, so here noise is, as we said, square root of what is the actual noise and the predicted one. The mean is calculated with x minus predicted noise by absolute. So this we know and you can see that mean plus a noise is also added. A small noise, which I told you, is added to it in order to if without this noise, what will happen? I think they have if you don't add a noise, how it actually gives you blurred images. That is also explained here. So we are using a method. If you look at the code, at least we can understand what they have used in. They are using a DDPM. And then this is for visualizing. This is, you can see this. They have just animated it. They are plotting, at different timestamps. You can see how the noise is done here. So it starts like this. The noise is, this is the training phase. That is the sampling phase. How it generates images. So for all the sprite images that we have downloaded from there, how they are just plotting the results which are just stored in there. So you can see. So this is how it works. So this is also an example where that extra noise is not added to it. Okay, so there we had mean plus the noise that we added. Here they are not adding the extra noise. So in that case, if you can see, so these are all done as different fine-tuning methods, experimentation. This is the same code when they executed without adding extra noise. It was like this. Kind of it did not learn because the what was expected and what training was given to it was from a random, from a Gaussian distribution. It has to pick up from pure noise. It has to pick up and learn. But then when we start reducing the noise, later when we are adding in the later time steps, we are giving a more clearer image, not the exact noise. So in order to maintain that equilibrium, in order to keep more exploration, we have added more. We add a small bit of noise also. It's just we have seen what is the equation that is used there. You can please go through this. GitHub has this clone of this. There are many diffusion models, and people have just used that models and they do different experimentation with this. So this is one. This is the base model. Let me just check. Neural network. Actually, I'm not going into. We can see the training. 1 minute. Even training also, the other two things I will just show you. That is how context is added here. See, this is a defined context. So we know, as we said, whether it is labels or it can be added as an additional vector. And we know that it can be added into the neural network. So here as embedding. So they have done that. After giving a context, they mean to say that the clarity is more. Are you able to see the screen? Actually, I am struggling with this Google Meet thing. Is it visible?
Yeah, ma'am, it's visible.
This is how we can embed some kind of a context to it to make it better. In fact, we are only able to see it visually without the context, and with the context, they are plotting it and all that. But we can use any kind of a metrics for evaluating how the images are done. And then controlling, as we said, this is just for the. 1 minute. So here, I think we have seen that for the controlling, we have, instead of using the DDPM, this is, I think what I meant, the same thing, extra noise and all that. So what was used earlier is DDPM. Here, I think they are using the DDIM method. So you can see, you can just change this method function only, all the rest is same. Instead of DDPM, here we are just not using the probabilistic way of doing it. They're skipping time steps here. So intermediate step size is equal to time steps. You can give 1 second. For I in range, time step 0 to minus step size. You can skip certain time steps and then how it works. So that's the only difference here, which I just mentioned about DDIM. And that was experimented and was given here. See, probably the, the quality was compromised a little bit. They have given some metrics, and we have seen, that confusion matrix and heat maps that are given there. So how it, there's a trade-off between the execution time as well as the quality of the images that are generated. So this is an overall idea of diffusion models, and maybe we can stop with this, or anything else is there in the PPT. I will just check. That's all. What do you say? We can wind up?
Yes, ma'am.
Okay. Thank you then. And some more code which I wanted to explain. Okay, you can try your own methods. Okay, and then it, as we said, it takes a lot of time. So even if it's on GPUs, as we said, I think all those basics, all of it's a final day. So you can try with the the GPU options that are given there. So anything else?
Queries, participants, please give. Any questions?
This is the final session of the whole FDP, 6 days.
Yes, ma'am. Yes, ma'am.
Okay. Participants are from other state also?
Yes.
Okay, good. Good number, no? You've got enough participants.
Thank you, ma'am.
Is it hybrid mode? Are there somebody coming there?
Hybrid mode.
Oh, so there are.
Stays offline. Stays offline.
Oh, first day. Okay. Okay, I think you've gotten just an overall idea of what is diffusion model. You can, move further in 2-3 ways. One thing is you can look at the different implementations. As we said in the beginning, you can at each step, you can go in for the optimal ones and build your own model and check how it works with the benchmark data sets. That's one thing. Or you can go and find out in the mathematical side, because they are all working on this, whether you want a stochastic models, or you can just look into that as research and then try to bring in some kind of a difference there and build and call it as your own diffusion model, and then you can keep working. That is also possible. Or it can be you develop something for a total, like how people have developed for a speech and only a text to speech, like a text to speech or speech to video, audio, something like that. Any specific, or as I said, any source, like if you want to, can you try synthesizing images for bathymetry data or any underwater sonar images, where generally we don't get enough data for work. So how can we use diffusion models for that? Can we embed any vectors based on the context or noise, any additional information you can use for generating new images? That way also you can work on this. So these are the different areas which I think which you can continue with diffusion models. Okay, so I think we can wind up. There are no queries.
Okay, ma'am. As we come to the end of today's session, I would like to express my sincere thanks to Dr. M.V. Chudi for delivering an informative and inspiring session. We truly appreciate the time and effort you have taken to be us with today. Okay, as we come to the end of FTP, participants are requested to kindly share the feedback. Anyone please give some feedback?
Maybe I can call out somebody here. Because it's a Saturday also. I don't know if people are available online.
Participants, please share some feedback here.
I can see some messages there. What do they give feedback for other sessions? Only for my session they are not answering. Is it like that?
All sessions.
Somebody has raised a hand.
Participants, please unmute your mic and give some feedback. Anyone, please give.
And it's about this session or whole FDP?
This session, this is the final day.
നീ അവിടെ അല്ലേ നിക്കണ്ടേ? അല്ല അവിടെ
Okay, dear all, here we conclude our 6 days online FTP on generative AI and building LLM. On behalf of CSC Department FISAT, I would like to thank all the resource persons who deliver very fruitful session. I would like to thank FISAT management to give us permission to conduct this FTP. Special thanks to Principal Dr. Jacob Thomas sir, Vice Principal Dr. Mini ma'am for all the encouragement and motivation. I would also like to thank Dr. Paul P. Matai, HOD CSC Department for all the support. I would also like to thank all the participants for your active participation and support. Thank you all. Certificates for participants will be provided within a 1 week. The recordings and PPT will be available on YouTube, and we will also share the drive link for access. Once again, thank you all.
Okay, thank you. I'll leave now.
Okay, ma'am. Thank you.
Thank you
so
so
much.
much. Thank you.